On June 2, 2025, Mount Etna erupted for the 14th time in just months, sending a 6.5-kilometer ash column into the sky and grounding flights across Sicily. But this was no ordinary lava. Scientists racing to the crater recovered glowing fragments unlike anything in Etna's long history, baffling lab instruments, defying earthly classification, and triggering a quiet panic among European experts. What did Mount Etna really unleash? And could this signal a deeper threat beneath Europe's largest volcano? This is the eruption that shocked the world. And what comes next isn't routine. At 11:24 a.m. on June 2, 2025, Mount Etna released a column of ash that rose more than 6.5 kilometers above the summit. European Space Agency satellites recorded the plume punching through the lower atmosphere, its shadow stretching for miles over eastern Sicily. Catania's radar screens lit up with warnings as the ash cloud drifted rapidly toward air corridors used by commercial flights. Within minutes, airport controllers triggered a red aviation alert, the highest level, halting departures and forcing inbound planes to circle or divert. Passengers waiting in terminals watched departure boards flip to delay and reroute notices. For Etna, this was the 14th eruption since mid-March, a pace that even seasoned observers found remarkable. Each episode had sent ash over vineyards, towns, and highways, but this plume's height and density forced a full-scale response. Remote sensors tracked its composition and spread, feeding data to meteorologists and airspace managers across Europe. In the control tower, teams followed standing protocols: monitor plume trajectory, reroute traffic, and coordinate with civil protection agencies. The disruption rippled outward. Delays at Catania triggered knock-on effects in Rome, Milan, and beyond. For travelers, the eruption was a sudden inconvenience. For scientists and aviation officials, it was a reminder of how quickly Etna can shut down the skies over Sicily, and how every eruption demands real-time decisions to keep people safe. The mountain's activity was being watched from above and below, but the true hazard was just beginning to reveal itself on the ground. On the slopes below Etna's summit, the eruption's true danger arrived without warning. A pyroclastic flow, an avalanche of scalding ash, gas, and shattered rock, broke free from the crater rim and tore downslope at nearly 140 kilometers per hour. Tourists who had gathered at overlook points minutes earlier scattered in panic, sprinting for the safety of parked vans and stone shelters. First responders shouted warnings, their radios crackling as the cloud advanced, swallowing the path behind it. The blast front blurred the line between day and night, a wall of darkness and heat. Yet, as the flow surged toward the lower flanks, the mountain's own shape became its shield. Valleys like the Valle del Bove, deep and steep-walled, caught the brunt of the current, trapping most of its force inside natural containment. The hot debris fanned out across the basin floor, sending up plumes of steam where it met patches of lingering snow. In the chaos, emergency crews tracked every movement, ready to evacuate if the flow breached the ridges. But the containment held. No homes or villages lay in the path this time. When the dust settled, reports confirmed no casualties. For those who witnessed it, the escape felt razor-thin, a reminder that on Etna, the border between spectacle and disaster can vanish in seconds. The valleys had done their work, but the ground was left scorched, unstable, and off-limits. Only hours later would the first scientists attempt to approach the new deposits, stepping onto ground still hot enough to melt the soles of their boots. Hours after the eruption, IASR NGV field technicians began their ascent toward the southeast crater. The ground was still radiating heat, each step measured and deliberate. Static crackled through their radios, cutting in and out as volcanic gases drifted across the slopes. The team deployed a drone, hoping to capture a closer look at the new deposits. Its camera managed just 12 seconds of footage before the signal vanished into the ash plume. 12 seconds that would become the only visual record of the eruption's most enigmatic zone. Navigating fractured ground and pockets of steam, the technicians reached the edge of a fresh channel. There, amid scattered debris, they located a fragment unlike anything they'd seen on Etna before. It glowed with an electric intensity, resisting the dulling effect of cooling air. Handling it required thick gloves and careful coordination. The sample was placed directly into a sterile vial, sealed immediately, and logged with GPS coordinates and a field timestamp. Protocol demanded no shortcuts. The vial was labeled, cross-checked, and entered into the custody log by 2 team members on site. By late afternoon, the sample began its journey down the mountain. At the transfer point, a courier from INGV Catania signed for the case under double lock, a routine reserved for material deemed scientifically or operationally sensitive. The van carrying the sample took a direct route to the laboratory, escorted by a second vehicle as an added precaution. On arrival, the vial was logged into the lab's quarantine area, its seal unbroken. This single shard, collected under the strictest procedures, would become the reference point for every laboratory analysis that followed. The chain of custody, though standard in theory, now carried unusual weight. In the hours between eruption and lab arrival, every step had been documented, every handoff witnessed. For the scientists at INGV, the integrity of this process was not just about science, it was about trust in what the mountain had delivered. Inside INGV's mobile lab, the control sample was placed beneath a UV lamp. The fragment responded with a sharp, visible glow, far brighter than any basaltic glass from Etna's long catalog of eruptions. Operators checked the logbook, then reached for a handheld gamma detector. The digital readout jumped immediately, climbing past the instrument's upper limit. A technician recorded the spike and flagged the entry. Gamma spike off scale, retest with backup. Standard procedures called for a second reading on a separate unit. The result was the same. No instrument drift, no calibration warning. Radiation levels were well above background, but not consistent with any known volcanic rock from the region. Next came crystallography. The sample was loaded into the X-ray diffractometer, the machine's arm sweeping across the vial to capture the internal structure. The resulting pattern bore no resemblance to Etna's typical basalt, nor to the global database of volcanic glasses and silicates. The internal note from the analyst was terse, unmatched signatures, a fingerprint from nowhere. Operators double-checked instrument calibration, running a standard before and after the test. Each time, the reference sample produced the expected result. The anomaly held. Field staff gathered around the screen, scrolling through the diffraction data. Years of routine analysis had trained them to spot contamination, instrument error, and the subtle fingerprints of altered minerals. This was none of those. The combination of UV fluorescence, extreme gamma response, and a crystallographic pattern with no match in terrestrial records forced a new protocol. The lab director ordered immediate isolation of the sample and a full suite of expanded tests. The urgency was clear. This was not a case of mislabeling or error. For the first time in decades of Etna fieldwork, the instruments themselves seemed to be telling the team that something truly new had reached the surface. Specialists at the GFC laboratory in Berlin received the control shard with a clear mandate: break down its elemental fingerprint, no assumptions allowed. The team prepared a series of ultra-clean splits, dissolving minute fragments in acid for inductively coupled plasma mass spectrometry. The first results arrived overnight, numbers that didn't fit any pattern in Etna's long geochemical history. Yttrium, cerium, and other lanthanides spiked far beyond the upper limits seen in the volcano's usual basalt flows. These elements, rare in surface lavas, are more often found in deep mantle rocks, or certain types of xenoliths, the geological stowaways that sometimes ride magma to the surface. The lab's lead geochemist flagged the data for urgent review, double-checking calibration standards and running blanks to rule out contamination. Every control came back clean. The anomaly held. Thermal analysis added another layer. When a sample was subjected to controlled heating, the material remained solid past 1,600 degrees Celsius. Etna's typical lavas begin to melt well below that threshold, usually between 1,150 and 1,250 degrees. the shard's refusal to liquefy, even as the furnace approached its maximum, suggested a structure more resilient than any volcanic glass or silicate in the regional record. GFZ's internal notes compared the behavior to experimental runs on high-pressure phases, minerals synthesized in the lab not found in surface rocks. The numbers forced a hard look at the possible origins. Either the eruption had tapped a pocket of material from deep within the Earth, or something about the blast had created conditions never documented at Etna. The data left little room for middle ground. As the results circulated among the European Volcanology Network, the search for an explanation only grew more urgent. The next step would be to examine the structure of the shard itself, looking for clues in the arrangement of its atoms. Paraspectroscopists received the control shard in a sealed case, accompanied by a digital request for immediate structural analysis. The lab's Raman spectrometer, calibrated against a diamond standard that morning, delivered results that startled even the most seasoned mineralogists. Instead of the broad, familiar signatures of volcanic glass, the spectra lit up with sharp peaks matching high-pressure mineral phases. Structures typically formed hundreds of kilometers below the surface, or in synthetic samples pressed in laboratory anvils. These peaks, clustered in the ranges associated with deep mantle polymorphs, appeared impossible for material that had traveled so quickly from Etna's interior to open air. The Paris team, led by Dr. Elodie Marchand, ran the analysis 3 times, each with fresh calibrations and new sample mounts. Every run returned the same improbable lattice signals. Marchand's internal memo, routed through encrypted servers, flagged the results as potentially paradigm-altering, pending replication and artifact exclusion. She attached raw spectra, calibration logs, and a request for blind verification by an external reviewer, a mineral physicist in Zurich with no prior involvement in the Etna investigation. Within hours, the encrypted thread grew dense with technical debate. Berlin's geochemists pressed for instrument logs and environmental controls. Catania's INGV team uploaded their own Raman data, which showed weaker but similar peaks. The Zurich reviewer, working from anonymized splits, confirmed the presence of high-pressure indicators, but cautioned that cosmic ray interference or detector drift could not yet be ruled out. Across the network, scientists weighed the risk of artifact against the implications of a genuine new phase. By the end of the week, the consensus was uneasy. The Paris spectra stood unreplicated in full detail, but the anomaly persisted across labs. Calls for open data sharing and blind retests grew urgent. The debate over contamination, calibration, and discovery was no longer private. Each encrypted message a record of science under pressure, and a signal that the story of Etna's June eruption was far from settled. Remote sensing teams began their review as soon as the eruption's ash cloud cleared the summit. ESA's Sentinel-1 radar satellites, scanning the volcano's southeast flank, detected a pattern of ground movement that immediately stood out. The data showed asymmetric inflation, localized bulging that pushed the surface outward and upward, crossing the deformation thresholds established after earlier collapse scares. These measurements weren't subtle. Over the course of just a few days, the southeast sector expanded by several centimeters, a rate that in past episodes has triggered internal evacuation alerts among hazard modelers. In the control rooms of Catania and Berlin, geophysicists pored over the interferometric maps, tracing the boundaries of the bulge. Their software overlaid the new data on reconstructions of Etna's ancient topography, and a troubling resemblance emerged. The current geometry, with its concentrated swelling and shifting stress lines, mirrored the models of Etna's structure just before a catastrophic flank failure some 7,200 years ago, a collapse that likely sent millions of tons of rock racing into the Ionian Sea. Infrasound arrays, tuned to the deep base of the Earth, picked up surges of low-frequency energy radiating from beneath the southeast crater. These acoustic signals, often associated with magma movement or structural adjustment, spiked well above background. Analysts flagged the readings. Such infrasound bursts have preceded slope failures and rapid depressurization events in other volcanic systems. For the satellite analysts and hazard historians, the evidence was plain. The volcano's internal mechanics were changing in ways that could not be ignored. With each new pass, the radar told the same story. Etna was not simply erupting, it was straining, reshaping itself, and testing the limits of its own stability. Municipal offices in towns like Zaffarana, Etna, and Milo became nerve centers overnight, their phones ringing with demands for clarity. Official bulletins arrived in rapid succession. 1 hour warning of possible evacuation, the next advising only heightened vigilance. Some families packed up and left for relatives' homes in Catania, while neighbors stayed behind, unwilling to abandon vineyards or livestock. In the same village, shutters closed and lights flickered on in kitchens, where people debated whether the mountain's threat was real or just another episode in a long Sicilian memory. A resident summed up the mood in a single line: "Etna is life and fear at once." The words echoed across doorways and in the anxious silence after evening news reports. No single authority could offer certainty. Civil protection agencies cited evolving data, pointing to the need for caution, but refused to order a full-scale evacuation. Local officials, caught between scientific advisories and community pressure, struggled to decide whose warnings to trust. While confusion spread among households, another current began to flow beneath the surface. Within days of the eruption, 2 foreign companies submitted exploration interest notices citing the region's strategic mineral potential. The timing stoked anger. Residents watched as outsiders treated the ongoing crisis as an opportunity, filing paperwork while ash still drifted over fields and families argued about leaving. The sense of order frayed. Some saw the rush to claim resources as a violation, others as a sign that the world's gaze had shifted from safety to profit. The mountain's threat was not just geological now, but social, splitting communities, testing trust in institutions, and leaving the question of who decides what happens next hanging in the air. On June 2, 2025, Mount Etna released a 6.5-kilometer ash plume and ejected a fragment that stunned the scientific community. Lab tests showed material with no match in any terrestrial volcanic database, emitting fluorescence under UV and withstanding temperatures above 1,600 degrees Celsius. The same shard displayed high levels of rare earth elements and crystal structures usually found far below the Earth's surface. Encrypted exchanges between European labs confirmed the anomaly. Meanwhile, satellite radar showed the volcano's southeast flank deforming beyond past emergency thresholds, echoing patterns seen before a massive collapse 7,200 years ago. Despite these facts, experts cannot say if this event marks a new phase for Etna or a one-time anomaly. As of late June, the control sample remains under review, and civil protection orders remain divided. The only certainty is that Etna's eruption has challenged what scientists thought they knew and left a region watching, waiting for answers that only time and further evidence can provide.